So, now that we know the point group, vibrational mode, and symmetric element, we're now going to move into the character table. To understand the character table, we must know the three things. We must recognize the symmetry operation, molecular properties and basic vector, and then characterize the symmetric behavior. If it is symmetric, we will assign it positive 1. If it is anti-symmetric, we will assign it -1 character. So, recognizing a symmetry operation, molecule confers precisely to the symmetry operation of the point group to which they belong. For example, if we take water molecule is H2O. Water conforms to the symmetry operation of the C2V point group. So the point group for the water molecule is C2V. The appearance of the molecule before and after the symmetry operation will remain identical. Then next we must know the molecular properties and basic vectors. These properties include your translation, rotation, vibration, and electrons behavior in the electronic orbitals. They are also known as basic vectors because they form basis for the understanding how the behavior of the molecule changes or what happens to the molecule under the symmetry operation. Then we have characterizing symmetric behavior. Characterizing symmetric behavior, we're going to give it a character. Symmetric behavior is categorized with positive 1 and antisymmetric behavior is categorized with the -1. These values represent the character of the property with respect to the symmetry operations. Now that we have the example of water, let's illustrate. We place the oxygen atom at the origin of the Cartesian coordinate system and then examine the behavior of the px orbital on the px orbital is this orbital on the oxygen atom. So if you perform a symmetry operation such as C2, which is rotation about the z-axis, this is your z-axis, this is your z-axis along the Cartesian plane, and we're performing the C2 operation, which is the rotation about the z-axis, we would rotate the molecule while ignoring the position of H and O for the present atom. When we perform this operation, the sign of the wave function will change, and we describe this as an antisymmetric behavior and give it a character -1. Because antisymmetric, we give it character -1. We can perform this analysis for all four operations for the C2V and then we can tabulate the results. So let's look at the example of the table. How you going to tabulate these results? So symmetry operations, we're gonna put this point group, which is your C2V in 1. Then we have different operations of water, which is your E. Then we have C2. Then we have rotation along the XZ plane. This is your mirror plane in X and Z plane. And then we have sigma V prime. This is in the Y and Z plane. So we did the number 1. We are looking at the effect on oxygen. We can write it here. To px orbital. Okay, so we will give it a this is unaffected, so we will give it positive character. This we said this is the antisymmetric, so we will give negative character. Okay, now this is, we said that this is the Z and X plane and this is the Y plane. So this operation, this is happening along the x and z axis. So x and z axis, so when we rotate along the x and z axis, it will remain positive, and then prime, this will take place in y and z axis. This will be antisymmetric, so we will give it a character -1. In this table, 1, we said this the molecule is not affected or unchanged, and then -1 will show that there is changed or reversal of the molecule. Now that we know that what is the effect of oxygen on 2p-y orbital, we can do the same for the 2p-z orbital along the z plane. We can perform the identity operation and see what happens. Then C2, then in what happened in the vertical mirror plane in the x and z plane, and then prime in y and z plane. So what will happen? These molecule in each plane will remain unchanged, so we're gonna give this character 1. Okay, similar to how we treat p orbitals, these are your p orbital, right? So this was the table we generated for the p orbital, 2p-y orbital and then 2p-z orbital. Similar to how we treated p orbitals, we assign characters to translation and rotation based on their behavior under the symmetry operations. For example, after performing the C2 operation, the direction of translation or rotation they can reverse, so it will result in a -1 character. Because remember, antisymmetric or reverse is -1 character. We give it -1. The character table for rotation, a rotation can stand for R along x-axis, y-axis and z-axis can be constructed like we constructed the table for the p orbital. When we talk about translation, it is depicted with symbol tx, where x stand for the x-axis. Then if we talk about ty, y is y-axis, tz along the z-axis. Each translation will represent a degree of freedom for the molecule in 3D space. Same goes for the Rx, so we can say here translation, we can assign Tx, Ty and Tz. Then rotation, Rx, Ry and Rz. Each rotation will also represent a degree of freedom for molecule in the 3D dimension. So these x, y and z are these x, y and z. Okay, let's describe translation along x-axis using the diagram. So we're gonna draw simple diagram. This is x, z and y plane. This is the rotation along C2. Okay, this is going under the C2 translation. Then this will be x, y, z. Okay, I'm gonna put this arrow here and I'm gonna put this arrow. This arrow represent the translation along x axis. Okay, like how we discussed the translation along x-axis, we can say that we can consider rotation also in the same procedure. So consider the rotation along y-axis. We can say if the we can give an example of a steering wheel of an automobile, right? So it will convert this from y-axis. If we are talking about the rotation along y, it will convert the molecule like this, right? So I can show you the rotation along the our y-axis in using the arrow. So this is the arrow here. We're gonna start here and we're gonna move from here till here like this, right? And this will give us arrow like this. So this is the rotation along y-axis when C2 operation is performed. So after the C2 operation, the direction of the turn of the automobile has been reversed. So from clockwise direction it is gone to the anti-clockwise direction. So we will assign this a character of -1. Now all this information we can again put it into the symmetry. Don't mind my writing. Symmetry operations, right? So we can put this in point group. We said I'm just writing G for the group, C2V, then we have the different operation, prime, okay. And then we talked about the effect of rotation along different axes, right? There were 3 axes. I'm gonna draw 3 columns. Okay, right. So I'm gonna write here effect of, then I'm gonna say y-axis, on y-axis, then about x-axis of rotation, about y-axis, effect of rotation about x-axis, and effect of rotation about z-axis. And then we're gonna look at each of the axes and we're gonna rotate it, and then we will come up with these value. So wherever it is -1, it means that it is going in the inverse direction or anti-clockwise direction, and wherever it is +1, it is remained unchanged. So this is your table for the rotation about the y-axis, x-axis, and z-axis on the water molecule. Okay, so now that we have all of this information, we can condense all the information into the one single table. So let's look at that table. That is called your character table. So this is your character table with all the information. Now I'm going to show you and explain to you all the different parts of the character table, and then how we're gonna see how we can read it. So starting with this corner, left hand side, top corner, here it says C2V. What does this mean? C2V, this represent the point group. Then EC2, mirror plane, in vertical mirror mirror plane prime. What is this? These are your symmetry operation which are arranged into the different classes. Okay, so this one was the point group. These are your symmetry operation arranged in different classes. And then next is this column here, A1, A2, B1, B2. What does this mean? These are your symmetry species. This one here, these are your symmetry species. These symbols are referred to as your Mulliken symbols and are used to describe symmetry properties of molecular properties in a shorthand way. So these symmetry properties of the molecular properties are referred to be an irreducible representation. They can't be broken down further or simplified further, right? Then we have this thing right here which says Z, RZ, X, RY, Y, RY. What is this? This is your molecular properties like translation and rotation assigned to their symmetry species. They are also called the basic function of irreducible representation, and you will always find 6 symbols here which are your XYZ. These are your XYZ, and then Rx, Ry, and Rz. These are all your symbol. They will be always here. This will describe the properties such as your rotation and translation. They represent the mathematical function, for example, your orbitals or your rotations, as we said. Okay, then what is this? 1 minus 1, 1 minus 1, 1 minus 1 minus 1, 1. These are your representation. A representation of the symmetry properties of certain molecular properties. This line is a representation of how translation in the x direction and rotation about the y-axis behave in the C2V point group summary. So, translation along x-axis, rotation along r mean rotation, y mean y-axis, behave in the C2V point group symmetry. This is actually a mathematical code and is found here in the simplest form, and therefore it is referred to as irreducible representation, or can be referred to as your symmetry species. Then this whole thing, minus 1, minus 1, 1. What are these? These are your characters. Okay, so then we talked about the Mulcanian or Mulliken symbols. Mulliken symbols like A or B, E or T. These represent for the these have special meanings to them, right? So let's look at some of the Mulliken symbols. A or B. This represent um one-dimensional representation. Then A is symmetric with respect to rotation about a principal axis, which is Cn. Symmetric. Then we have B. It is anti-symmetric with respect to rotation about a principal axis again. Then there is another symbol called E, which stands for doubly degenerate representation. And then lastly we have T, which represents for 3D representation. Then in the character table we have subscripts like 1 and 2. These subscript refers to the symmetry with respect to again C2 axis perpendicular to the principal axis or to the vertical plane of symmetry if there is no C2 present, where 1 stands for symmetric, this is symmetric, and this one, number 2, stand for anti-symmetric. There are different things also which we can also see prime in the character table. So if there is 1 prime, then it means symmetric. If there is 2 prime, it means anti-symmetric. These are all the characteristics of the character table. Okay, in the point group, which have a center of symmetry, the subscript G and U also are used. So you can say point group which have a center of symmetry, subscript G and U stand for. G is for symmetric, and U is for antisymmetric. This is the with respect to an inversion. So they are always talking about the inversion where they are using the G and U um, subscript in the character table. Okay, so this is all about the characteristics of an character table, and we talk about that number one here represents the point group. Then we have symmetry operations here, this one, and then these subscript represent the Mulliken symbols, and then we discussed characters of an irreducible representation like -1, 1, and then we saw the function of symmetry symbols for Cartesian coordinates and rotation, which are these z, x, y, z, r, x, r, y, r, z, and then lastly the function of symmetry symbol for square and binary products are here.